Good morning, everyone. Today we're covering Unit 1, Lesson 10, Review. So we're going to look at what we've done so far in this unit and then just kind of summarize each of those things. So we'll start with expand and simplify. So expand and simplify your polynomial expressions. We would have seen this in grade 10 and grade 11 math as well. Solve polynomial equations by factoring to identify your x-intercepts and your zeros. And if we can't factor, we would say, or use the quadratic formula. Okay, use polynomial functions to model real-world applications. So we're just talking about word problems there. Real-world applications. Solve equations of the form x to the power of n equals a by taking the nth root. We covered that in this unit. And then also when you're looking at formulas, what are the roles of the constants and the variables in those formulas? We talked about setting something to a constant to create a linear equation or setting a value to a constant to create a quadratic equation. We also talked about determining the value of a variable by substituting in or rearranging. So two ways to solve for an unknown, either substitute in and then solve or rearrange for that unknown and solve. And then finally solving multi-step problems that arise from the real-world applications. So let's take a look first at expanding and simplifying. We'll do one together and then we'll set up the next one and I'll have you guys pause it and try a few. So expand and simplify. When we expand and simplify, we want to use that distributive law and FOIL where it's appropriate. Okay, so our first question, 4 times 2x plus 7y minus 3 times 5x minus 2y. So we're going to distribute what we have on the outside of our brackets to the inside of our brackets. So 4 times 2x is 8x, and 4 times 7y is 28y. From that, we'll subtract, so we have a 3 minus 5x, so that's a minus 15x, and then a negative 3 times a negative 2y is a positive 6y. And then we'll just combine our like terms. So 8x minus 15x is going to be a negative 7x, and 28y plus 6y is going to be 34y. So I'm just going to set up the next one, and I'm going to have you guys pause and try B and C on your own. So remember, when you have a binomial raised to a power of 2, what does that really mean? Well, it means that we're taking that bracket and we're multiplying it by itself. So it's the same as saying the 4x plus 3y times 4x plus 3y. Go ahead and pause this video and see if you can finish expand and simplifying B, and then go ahead and try C as well. So there are the solutions for the next two. We made sure to distribute that number outside the brackets for B, inside the first brackets, and then we foiled these binomials, and then we continued to expand and simplify from there. On question C, we did the same as well. We expanded, or we distributed from the innermost part of our bracket, so we distributed the 3y into the brackets, and then we distributed the negative 7y over here. And then after we did that, we continued to distribute and expand and simplify. You can see the solution we got. So number 2 says we're going to factor the polynomial expression to identify x-intercepts and zeros. So factor and state the zeros for each of the following, then graph the function. So we might need to find more information than just the zeros, but we'll start by factoring to find our zero. So our first function is f of x equals x squared minus x minus 12. So we should be able to factor using SPF. So we need two numbers whose sum is a negative 1 and whose product is negative 12. So hopefully we can see that that's going to be a negative 4 and a positive 3. And we can say f of x equals x minus 4, x plus 3. So our zeros will be 4 and negative 3. So these are our zeros. Okay, Aside from our zeros, though, we're going to need to find our vertex in order to graph this. So we'll start by finding the x value of our vertex. So we find the x value of our vertex by finding the midpoint of our zeros. So I'm just going to write midpoint of the zeros. Okay, so 4 plus a negative 3 is 1. 1 divided by 2 is just 2. So we can say 0.5. Then we need to find the y value of our vertex. So I'm going to take that 0.5 and I'm going to plug it back into my factored form of my equation. So I have 0.5 minus 4 and 0.5 plus 3. So the y value will be a negative 3.5 times a positive 3.5, which equals a negative 12.25. So we can say, therefore, our vertex is 0.5 and a negative 12.25. Okay, so let's graph that. So let's first graph our zeros. So our zeros are at positive 4, 1, 2, 3, 4, and negative 3. And then our vertex is at a positive 0.5 and a negative 12.25, which is going to be somewhere down here. Let's just move our page up a little bit. Somewhere down here. So we'll connect the dots to try to make a curve for our parabola. Okay, so there's that function. Let's look at the next one. So if we have f of x equals x to the power of 4 minus 1, we can factor that as well. We have a difference of squares. So we're going to factor using a difference of squares. Okay, so if we have a difference of squares, we can just take the square root of both of these, square root of x to the power of 4, and square root of 1. So the square root of x to the power of 4 is x squared, and the square root of 1 is 1. So we're going to have a minus version of that, and we're going to have a plus version of that. So x squared minus 1 and x squared plus 1. We can further factor that x squared minus 1. That'll be x plus 1, x minus 1. We can't factor that x squared plus 1 anymore. So from there we can identify our zeros. Well, x plus 1 is going to have a 0 of negative 1. X minus 1 is going to have a 0 of 1. This x squared plus 1, if we set that equal to 0, and then we move over the 1, so x squared equals negative 1, we can't take the square root of a negative 1. Right? If we try to take the square root of a negative 1, that doesn't work. Okay, so there's no 0 from that factor on the end there. So our zeros are a negative 1 and a positive 1. Okay, so we can plot those zeros. We have a 0 at negative 1, and we have a 0 at positive 1. Now for this one, it's not a quadratic because it's not to a power of 2. So we're going to have to do some test points to find additional points on this graph. So let's do test points for x and f of x. So if we substitute it in, we'll just substitute in negative 2, negative 1, 0, 1, and 2. So if I substitute a negative 2 in, well, a negative 2 to the power of 4 is going to be a positive 16 minus 1 is 15. And negative 1 to the power of 4 is just 1, 0. I'll substitute in the rest of my values, and here's what we should get. Okay, so if I sub those values in, that's what I'll get for my y value. So I'm going to plot those points. So at negative 2, we're going to have a y value of 15, so somewhere up here. Negative 1 is at 0, 0 is at negative 1, 1 is at 0, and 2 is back up at 15, somewhere up there. So there's that quartic function. X to the power 4 creates a quartic function. Okay, let's continue with you. So factor and state the zeros of each of the following problems. So I'm going to do a couple with you, and then I'll get you guys to pause the video and try some on your own. So the first one we have here, we have f of x equals negative 2x squared minus 3x plus 6. So we have to think about how can we factor this, okay? And we could try to do SPF, so let's try to do SPF. We're going to need two numbers to add to a negative 3 and multiply to a negative 12. So if I think about my factors of 12, I have 1 and 12, 2 and 6, and 3 and 4. I don't think I can get any of those to add or subtract to a negative 3, so there's no factors that are going to work. So we're going to plug into our quadratic formula. So remember, that's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and we can identify our a, our b, and our c right in our equation. So x equals a negative b, so I'm going to put negative 3 in brackets, plus or minus the square root of a negative 3 squared minus 4 times my a value, which is a negative 2, times my c value, which is 6. All of that is over 2 times my a value of negative 2. So we'll start simplifying this where we can. A negative negative 3 is a positive 3. And then in my brackets here we have 3 squared, which is 9. And then if we simplify the rest here, negative 4 times negative 2 is a positive 8. 8 times 6 is 48. So we have 9 plus 48. So this would all simplify to 57 all over negative 4. Okay? And then we can split this into the two solutions. We're going to have one that's going to be 3 plus radical 57 divided by negative 4, and one that's going to be 3 minus radical 57 over negative 4. And I just want to write or in here, right? We got two solutions. So if we calculate that, 3 plus, we should get x equals a negative 2.64. And for this one, we're going to get x equals 1.14. Okay, so that's factoring to find our zeros using the quadratic formula. So these are your zeros. Let's look at one other equation we have here. We have a cubic. So I know I can't factor using SPF or any of the trinomial factoring we've looked at. So we're going to try factoring by grouping. Because if we have 4 or more terms, we're going to factor by grouping. So I'm going to group my first 2 terms together and common factor out of them, and then my second 2 terms together and factor out of them. So for my first 2 terms, I'm going to common factor out a negative x squared. That's my greatest common factor. Always good to pull the negative out as well. So if I take a negative x squared out of negative 2x cubed, I'm going to have a positive 2x left. And x squared divided by negative x squared is going to be a minus 1. My second 2 terms, I'm just going to common factor out a 1. Nothing else to pull out there. And then you'll have 2x minus 1. Now I can pull out that common bracket we've created. So we have this common bracket that we can pull out of those groupings. So we're going to have 2x minus 1, and then we're going to have a negative x squared plus 1. Okay? And we can rewrite that negative x squared so that we don't have the negative as our leading coefficient in that factor. I'm going to rewrite that as 1 minus x squared. And now I can factor that. That is a difference of perfect squares. So you have to start to be able to recognize how we can factor these different polynomials. So we still have 2x minus 1. And then this 1 minus x squared is going to factor to 1 plus x, 1 minus x. So if I wanted to identify my zeros, I'm going to set each of them equal to 0. And then solve for x. So in this case, you're going to move the 1 over by adding it, and x is going to equal 1/2. Over here, 1 is going to equal x. Sorry, -1 is going to equal x. And over here, 1 is going to equal x. So those are your zeros. Go ahead and pause the video and try to work through E and F on your own. Okay, so there are the solutions for E and F. In E, we factored by grouping again, and then we found that our x-intercepts were -2 and +2. You can see that we got a +2 for x-intercept 2 times, so we only need to list that as an x-intercept once. In F, we common factored, and then we used SPF, or decomposition, to continue factoring, and you can see that we found our x-intercepts were a -1/2, 0, and 4. So moving right along, we're going to start modeling real-world applications with polynomials. So it says a shipping crate measuring 2x plus 3 meters by 3x minus 1 meters by 2x plus 5 meters. Find the simplified expression for its volume. So remember, volume equals length times width times height. So we have our length, our width, and our height. We're just going to substitute in to that equation. So we'll have 2x plus 3 times 3x minus 1 times 2x plus 5. So again, pause the video and go ahead and expand and simplify this to get a simplified expression for the volume. So after you expand and simplify, you should get the volume equals 12x cubed plus 44x squared plus 29x minus 15. With our review. All right, then we looked at solving equations in the form this x to the power of n equals a, and we looked at taking the nth root. So we'll try a couple together, and then you guys can pause and try on your own. So remember, if we're taking, when we're solving algebraically, we need to talk about how many solutions we're going to have. But first, we're just simplifying a root of a number. So if we had the third root of 64, we could also say, remember, the root is the same thing as raising it to a fractional exponent. So you could also say 64 to the 1/3. But either way, that equals 4. If you had 16 to the 1/4, you could also say that this is the 4th root of 16. Let's make that a little bit clearer. Fourth root of 16, and that equals 2. Okay. When you have something like you do in C here, we first have to take the third root of 27 and then raise it to 4. So let's just write, we want to take the root and then the exponent or power. So the cubed root of 27 is 3. We're going to raise 3 to a power of 4. And 3 to the power of 4 equals 81. You guys pause the video and try the rest of these examples. So there's the solutions for the rest of them. If you look at, in particular, E, recognize that sometimes you're not going to get a nice rounded number. So 12 to the power 1/3, we get some long decimal, and so sometimes it'll specify what you need to round to. And here it says to round to 1 decimal, so we're just going to change that to 2.3. And the same is true for F. So it says to round to 1 decimal, so we will change this to 16.7. All right, find the real roots for the following equations. Round your answers to 1 decimal place when necessary. Remember, even exponent, you're going to have 2 solutions. If we have an odd exponent, you're only going to have 1 solution. So keep that in mind when you're solving these. So if we have x to the power of 3, we need to get rid of the exponent. So we need to raise it to a power of 1/3, because 3 times 1/3 is just 1. That'll become x. And 8 to the 1/3 is 2. Same is true here. So again, x squared, we could raise that to a power of 1/2, but we know raising something to a power of 1/2 is the same as taking the square root of it. And because this is an even exponent, we're going to have a plus or minus 7 for our answer. Go ahead and pause the video and finish the next two. So there's the solutions for the next two that you hopefully worked out on your own. The next thing we talked about is the role of constants and variables in formulas and how they change what kind of equation we're dealing with. So the formula d equals vt plus 1/2 at squared, where d is the distance traveled, v is the initial velocity, a is the acceleration, and t is the elapsed time. So determine the acceleration in meters per second squared if d equals 184, v equals 5, and time is 8 seconds. So it says sub in and then isolate. So we're going to substitute in first. We're going to use that strategy of substituting in. So into our equation for d, we're going to have 184. And that's going to be equal to v, which in this case is 5, times our t value of 8, plus 1/2, times our a value, we don't know a right now, times our t value, which again was 8 squared. So we're going to now simplify and then rearrange to solve for a. So 184 is going to equal 40 plus, well, 8 squared is 64, and 64 times 1/2 is going to be 32a. So now we have to start doing some rearranging. So I'm going to move my 40 over to the other side. So we're going to have 184 minus 40 equals 32a. So this will be 144 equals 32a. And then finally, we're just going to divide everything by 32 to continue isolating that a. I'll just finish this over here. So 144 divided by 32 is going to be 4.5 equals a. So therefore, the acceleration is 4.5 meters per second squared. Okay, the second part says to rearrange the formula for r and then substitute. So this time we're going to look at the strategy of rearranging before we sub in and see how the strategies are different. So if v equals 50 centimeters cubed and h equals 2 centimeters, find the radius. So again, we're starting with the volume equals pi r squared h, and we're trying to isolate for r. So I'm going to start by dividing both sides by pi h. That will leave me with r squared. Okay, I'm going to substitute in from here because we can see that what we've created now, we have r squared. This is a quadratic relation we've created. So we'll substitute in what we know. So our volume is 50, and our height is 2, and that's going to equal r squared. So then I'm going to take the square root of all of that. To get rid of that square on the other side. And if we calculate the square root of 50 divided by 2 pi, under that radical we should get 7.96. And then if we take the square root of that, you're going to get 2.82. So therefore, the radius is 2.82 centimeters. Okay, so let's take a look at the role the variable constant play when we're working with formulas. So which variable in the formula would you need to set as a constant to generate a linear equation? So remember, our formula was v equals pi r squared h. All right, and when we substituted in for h, we ended up generating a quadratic equation. So if we wanted to generate a linear equation, we'd have to substitute in for radius, because we'd have to sub a number in there to get rid of that squared. If we wanted to generate a quadratic equation like it's asking in C, we need to set height to a constant. We need to plug some value in for height. Okay, finally in the review, we're going to look at solving a multi-step problem. So kind of pulling together lots of the things we've talked about with polynomials, as well as just some real-life application. So Stephen is building a deck at the cottage. The length of the deck will be 18 feet, and the width will be 9 feet. Stephen can only purchase 12-foot boards that have a width of 6 inches and a thickness of 1 inch for $15.40 each before taxes. What is the minimum number of boards that will be needed for the job? So let's first draw what this deck is going to look like. So it says the deck is going to be 18 feet by 9 feet. So let's first figure out, well, what's the area of the deck then? It's going to be our length times our width, which in this case is 18 times 9, which is 162 square feet. Now it says that we can use boards that are 12 feet, and have a width of 6 inches. So keep in mind that everything so far has been in feet. So let's make sure that our width is in feet as well. So 6 inches is the same as half a foot. So these are going to be 12 foot by 0.5 feet. If I think about putting the deck board on here, I should be able to get a 12-foot piece along the length of the deck, and then I should be able to get, so one 12-foot piece, and then we should quickly be able to figure out, then we could stick a 6-foot piece there. So we could cut a 12-foot piece in half. So really each row we could do 1.5 boards. Which would mean we wouldn't have to waste any of the boards. Theoretically, there might be some waste, and we can talk about that. But we can see that if we do one 12-foot board and then a 6-foot board, then we could just bring the other 6-foot board down and then do another 12-foot board. Okay, so we shouldn't have any waste. So we should think about, okay, well, what's the area of one deck board? That's going to be length times width. And we know that the length is 12 and that our width is 0.5. So the area of a deck board is going to be 6 square feet. So we need to figure out how many boards can we get into the deck. So we can take 162, because that's the area of our deck, divided by the area of a board to figure out what's the minimum amount of boards we could use. And I'm just going to write that in a different color. So 162 divided by 6, we should be able to fit or need at least 27 boards, okay, to fill that deck. What is the total cost before taxes for the job? So if the minimum we choose to buy is 27 boards, it says that they cost $15.40 per board. So that's going to equal $415.80. Are there any other considerations when planning this job? Well, like I said, we're kind of assuming the bare minimum here. We could do 1.5 boards each row, no waste. So we're assuming that nobody's making any mistakes. So some things to consider would be waste or mistakes maybe when we cut the wood. Something else we should consider with changing the weather, the wood could shrink or expand. Right, depending on if it's summer or winter, the wood will shrink or expand. Should also consider how you want to lay out the deck. Okay, whoever's installing, do they want them all lined up, or do they want them staggered? So sometimes people prefer the boards to be a certain way. And then finally, sometimes something else to consider, sometimes there's some spacing between right? There might be like a 1/2 inch gap between the rows. So those are just some other things to continue. So that's our review for today. It was a long note, but go ahead and try some of the practice problems that go along with this unit review.